So we just agreed that we will measure uncertainty by the minimum number of bits required to represent a source. So let's return to our Google Server example for the running example, the email client. So how does Google Server actually complete our emails? How does the Google email Gmail client complete our emails? So what probably it does is it goes over all the emails that I have composed and finds and looks at the phrase that I have written and finds the phrase that follows it most of the time. Okay, so suppose that it has a list like that, and suppose that it knows that there is a phrase which follows this particular word half the fraction of time. So among all the time that it has seen this phrase, the following phrase comes up half the fraction of time. The next one comes 1/4 times, and the next one comes 1/8 time, 1/16 times, and so on and so forth. So suppose it has such a list with such likelihoods, half, 1/4 assigned to it, and it has 256 such possibilities. So that's, suppose it has already built this model. This is what we can think of the probability model that Google has built for my email. So it will represent all these phrases, and the first phrase has a likelihood half of occurring, which is a very high likelihood. Half the time I complete my emails after sorry I say for inconvenience. So let's say with half the times. Then the next phrase comes 1/4 of the times. The next one comes 1/8 of the times. Next one 1/16th. Next one 1/32, and the remaining phrases all come equal number of times. So let's see what is this probability. So we have half plus 1/4 plus 1/8 plus 1/16 plus 1/32. What is that sum? So you can quickly check that this remaining probability is so how many symbols are we left actually? So we have 5 symbols here. So these are 5 symbols, and we have 256 possible symbols. So we are left with another 251 symbols. Okay. And all of them come with equal probability. So 1/251 is the probability of the remaining guys. Okay. How much probability? So there are 251 symbols, each with remaining probability. How much probability remains? Half plus 1/4 plus 1/8 plus 1/16 plus 1/32. So that's you can quickly check that this remaining probability is 1/32. Okay. Because probability is sum to 1, so you can check that this remaining probability is 1/32, and it's spread equally among the remaining 251 symbols. So these are all very less likely in comparison to this first 5 symbols. Okay. So given that it already knows that this is the likelihood of these phrases, how should Google store these phrases? And how should anyone store these phrases so that the number of bits used are as small as possible? So let's think of some very simple schemes. Let me start with the simplest scheme that perhaps comes to your mind. We make a giant lookup table. Okay. So this lookup table has 2 columns, record number and phrase. So it puts a record number 1, 2, 3, and then it puts the phrase corresponding to it. How many records are there? Well, we said there are 256 possible phrases. You can represent them using 8 bits, so that's 1 byte. So you associate each phrase with 1 byte representing that phrase, the phrase number. So this particular method requires 1 byte or 8 bits to store all the phrases. Okay, but then can we do better? So here is another very simple idea. Why did we just make 1 table? Why don't we make 2 tables? Okay, what do I mean by this? So we first use 1 bit. So we use 1 bit to represent which table you should go to. So there are 2 tables that you have stored in your computer, and first for each symbol, first you figure out, you use 1 bit to indicate which table to go to find this symbol. Okay, and then in both these tables you have different symbols. So for instance, this symbol with probability half and probability 1/4 can go to table 1, and the remaining symbols can go to table 2. So you need 8 bits to represent this remaining symbols. You can check this. You cannot do it less than 8 bits. Actually, there are 254 symbols. at least need 8 bits to represent them. Okay, and these first table only has 2 symbols, so you only need 1 bit to represent them. Okay, so what is the worst case number of bits that you use here? Well, in the worst case, you will have 1 bit here plus 8 bits here, 9 bits. So worst case you can check is 9 bits. Okay, so each symbol gets represented by which table the symbol is in and what's the entry number in that table. So that will take 9 bits for all the symbols in this table too. Okay, but it only takes 2 bits to represent symbols in this table 1. It has just 2 symbols here. Okay, so what's the average number of bits that is used? Okay, so average number of bits. First, 1 bit must be used for all the symbols. So this 1 is with probability 1. Maybe I'll do it in a slightly different way, this calculation. So what is the average number of bits? These first 2 symbols, this first symbol with probability half, it uses 2 bits. 1 for the table and then 1 for the location inside the table. Then the next symbol, which has probability 1/4, again uses 2 bits. And all the remaining symbols use 8 bits. What is the remaining probability? Another 1/4. So use 8 bits. So what's the total number of bits? It's so this is 2 and then 1.5. So 2 plus 1.5. Okay, so that's 3.5 bits. So very interesting. This very simple scheme, although in the worst case is worse than the single table scheme. It uses 9 bits in the worst case. But on average, it uses much fewer bits. It only uses 3.5 bits. So that's something very interesting, and this is the kind of thing we want to do. We want to use as small number of bits as possible on average. In constructing these tables, I just gave you this answer, but if you try to think of how would you place the symbols in the table, it will be a very interesting exercise. So I'll give you the heuristic that I went by when I gave you this answer. What I thought was that I'll take the symbols which have large probability, in this case the first 2 symbols, and put them in a very small table, so that I can represent them with fewer bits. And I'll take the symbols which have very small probability and club them together in a separate table. That was the heuristic I went with. In fact, for all these symbols in table 2, I end up using much more bits than the simple representation by 1 byte, okay, 8-bit representation. However, collectively their probability is very small, just 1/4. Okay, so I pay extra here. Sorry, I think this calculation is not correct, but its conclusion is correct. So this should be 9 because I used 9 bits here, and so this turns out to be 3.75 bits. Okay, right. So I pay extra here. Instead of 8, I have 9 bits for these symbols. But I save on the other bits significantly, and overall average comes down from 8 in the single table case to 3.75 bits. Okay, so that's the idea. Now, is this a good assignment? Well, we can try some more things. Why did we assign just 2 symbols to the first table? What if we take 4 symbols for the first table? So now you have these 4 symbols in the first table and the remaining in the next table. So remaining symbols all will require 9 bits, and the collective probability is 1/16. So you can do this calculation. Now if you do that, the average length comes down even further. It comes down to 3.44 bits. Okay, so what's the end of this? You can keep on doing this. Can we have 3 bits for the first table? Basically, can we put 8 symbols in the first table? Now if you do that, you will see that the average length is 4.15 bits. Okay, so what's going on here? So we see that there are various options based on how we arrange these symbols in our tables, how we store them, and different schemes will have different average lengths. In fact, if you think a bit deeply, you will be able to convince yourself that this second scheme, which uses 2 bits for the first table and 9 bits for the symbols in the second table, so it will use 3 bits for symbols in the first table, 1 for table and location, and 2 for location inside the table, and 9 for the second table. This particular scheme here, this one here, is actually optimal. You can't do better than 2.44 bit, it turns out. Okay, and this is not so difficult to see. You can think about it. Okay, But there are all these other schemes which also look reasonable. And one thing is there for sure, that if we don't design the scheme by keeping the probabilities in mind, then our performance will be the same as the worst case performance, which is just 8 bits in this case. And the average is also 8 bits. So, and when we design schemes keeping the probability, the frequency of all these symbols in mind, we can do much better. We can bring down the average performance to 3.75 bits if we just try some naive thing, and if we are a little bit more careful, like in the second scheme here, we can bring it down to 2.44 bits. Okay, so this is just one example we saw. Let's continue with this example. So next thing you should ask yourself is, why just 2 tables? Why did we just use 2 tables? Why not 5 tables? Why not multiple tables? So we can do that. So we can make 4 different tables. Okay, so now we use 2 bits to represent the table number. So there are 4 different tables. They can be represented by 2 bits. 0, 0 is table 1, 0, 1 is table 2, 1, 0 is table 3, 1, 1 is table 4. And then you can try to think which symbols you'll put in these tables. At this point, I'll urge you to pause the video and try to think of this scheme by yourself. Try to come up with this assignment. How will you place the symbols in the across the tables, so that the average number of bits used to represent the symbol is as small as possible. Okay, I'll be giving this answer now, but I urge you to pause the video and think about it. Okay, so now that you have thought about it, so table 1, hopefully you agree with this. So now there are 4 tables, and what I'll do is I'll keep this heavy symbols, half and 1/4, in table 1. This will require 1 bit to indicate their location inside the table, because they're just 2 symbols. Another 2 symbols I'll keep in table 2, 1 bit to indicate their position inside the table. This table 3, I put 1 single symbol. So how many bits do I need to represent it? Well, 0 extra bits. If you go to this table, you know that this is the only symbol there. So no extra bit needed to represent this location there. And then the 4th table has all the remaining symbols. Okay, so we have already consumed 5 out of 256, so 251 symbols remain, and we use 8 bits to represent all of them. Once again, the rationale is same as before. We use we take the heavy symbols and put them in one table, and then the next heavy in second table, and so on and so forth. And all these light symbols, 251 of them, are clubbed together in a single table. All right. So 2 bits per symbol are now required for sure, plus extra based on which table are you in. So if you do this calculation, you can check that the average number of bits now comes out to be 3.25. So still worse than our 2.44, but 3.25, which is not bad. Okay, but this can be improved easily. Okay, so you can try another thing. Instead of putting half and 1/4 in table 1, you can put half. You can put this half alone in table 1, and if you make this small change, you will see that it improves to 2.72. So I'm just working out some example ideas here to see how different schemes can come about. Okay, so let's take another view of this multiple table scheme. So we can think of these tables themselves, the tables containing multiple symbols themselves, as a super symbol, which represents a group of symbols. Okay, and the probability of this super symbol can be thought of as equal to the sum of probabilities of all the symbols inside it. In fact, this view leads to what is called the Huffman code. We'll come to that later in this course. So Huffman code is a very popular code used for compression. It's well, it came out. It was the first optimal code for minimizing the average length. It is in fact still the only optimal code, and there's a story behind it. So Huffman was a master student when Elias, I think, raised this question about finding the optimal code in his class, and Huffman found this code as an answer to that question. So for all the master students taking this course, hopefully you will invent some new things by the end of this course. All right. So how do we view Huffman code? As I said, we'll come back to it in greater detail later. But here is a simple way of seeing that. Here is an alternative representation of those tables. So we are thinking of tables as symbols. So first table has the first symbol is half, and the second symbol, which is now itself a super symbol, is a table itself. This is table 2. So in the first table, you think of this as having just two symbols: half, the symbol corresponding to half, and the super symbol which we call table 2. Then inside table 2 there is another symbol which has probability half, and the super symbol which is now table 3, and so on and so forth. Okay, you can also view this entire arrangement by a what is called a graph. So you start with the root node. On the left side you put the symbol with probability half. On the right side you put a lot of other symbols. This is the super symbol table 2. So you go here now, and this guy has two symbols, one with probability 4th. On the right side you have this super symbol with all the remaining symbols. Again, left side 1/8 and right side super symbol with all the remaining probabilities. This table 4. So 1/16th, and then right side with all the super symbol, and so on and so forth, 1/32. And now here you have this single table 6 which has all the remaining symbols. And so you can represent it by this tree, and then what you can do is just go over this tree thinking of left side as 0 and right side as 1, and you just start from this root and reach to these so-called leaves, and this path represents the the bit assignment for each of these symbols. So you will get multiple you will get binary representation of all symbols. So half, the symbol with probability half has representation 0, symbol with probability 1/4 has representation 1/0, symbol with probability 1/8 has 1/10. Okay, so starting from this very simple lookup table scheme, we can quickly come to this much more sophisticated scheme. And when you calculate the average number of bit, it turns out to be 2.03 now. So this is better than anything we have seen till now. In fact, what we can show is that this is the minimum average length that you can have for this particular probability distribution, and it is attained by Huffman code. So we'll return to Huffman code later, but this example was to point out to you that if you think about the frequency with which different symbols appear, then you can have very clever compression schemes. Okay, let's take another view, okay, of the same scheme. Okay, so by the way, this is almost the Huffman code. You can do something slightly different, and we'll come back to that later. So you can do another. Let's go to another view of the same view. Okay, let's take another view. So here is another assignment. So this symbol with probability half is the heaviest symbol. What I'll do is I'll assign the shortest sequence to it. So which is the shortest binary sequence? Well, it's a one length sequence, 0 or 1. So we'll assign 0 to it. Then we'll go to the next symbol, the next highest probability symbol. This has probability 1/4, and assign the sequence 1 to it. Then we'll go to the next highest symbol and assign the next shortest available binary sequence to it. This time it is, so you've already used 0, you've already used 1, which is the next shortest binary sequence. Well, all the sequences of length 2 are remaining. So you assign the sequence 0, 0 to it. Then 0, 1 to this 1/16 probability symbol. 1, 1 to this 1/32 probability symbol. And then all the remaining symbols, you assign this sequences of length 8. So what's the average number of bits? So half, with probability half, the length is 1. With probability 1/4 for this symbol, the length is 1. With probability 1/8, it's 2. 1/16, 2. 1/32, 2. And then all the remaining symbols have length 8. And you compute this. And this average length is the shortest we have seen so far. It's 1.44. Okay, it's a very small length. So where does this improvement end? Okay, so all these schemes are there, and we started with a very basic scheme. It had average length of 8, which was also the worst case length. And then we tried many things, and just thinking out loud, and we came to this final scheme which has average length of 1.44 bits. Okay, so it seems this is even lower than the Huffman code. Now Huffman code has more structure than this kind of assignment. We'll come to that later. For some practical reason, Huffman code is preferred over codes like this. But nonetheless, we came up with a code which has very short assignment, just 1.44 bits. Okay. Okay, so where does this improvement end? So we will think about that question, because we want to answer this question to figure out what is the minimum number of bits required to represent a source, and that's a measure of uncertainty of the source. But let's summarize the lessons we learned from this example. Okay, so remember that two table construction where we took the symbol with probability half and 1/4 and put them in table 1 and the remaining in table 2. What we saw there was that and we saw that just with this small split we were able to get 3.75 bits instead of 8 bits. The idea is that most of the mass can be in very few symbols, and these are the ones we have to focus on. We can ignore the symbols which have total probability small. Okay, in this case there were this 253 symbols with total probability 1/4, and so we don't have to focus on them. What is more important is these two symbols which constitute 3/4 of the probability. Okay, so it is important to think of the high probability symbols, and you can maybe in the beginning ignore the small probability symbols which are very rare, and you can be inefficient in representing them. So going back to a Google example, Google probably knows that I have 4 or 5 answers which I usually choose to complete that sentence, and it will assign very short lengths to all those answers. It will assign maybe 2 bits or 3 bits. So 5 answers, let's say, so 3 bits to them. And then there are hundreds of other answers which are very unlikely to come, and it can be very inefficient in representing them. That's one nice scheme. Okay. The final scheme we presented, where we just, what was the final scheme we presented? What we did was we arranged the probabilities in their decreasing order, took the symbol with highest probability, assigned to it the shortest available binary sequence, then went to the next symbol, then assigned to it the shortest available binary sequence. This scheme is not practical because you have a different symbol for 0 and you have a different symbol for 0, 0. So there are some problems with those kind of schemes. However, and it's also not practical because this assignment takes a lot of effort. You have to sort all the probabilities of all your symbols, which can be a large number of symbols. And sorting is a computationally expensive operation, can be a computationally expensive operation. And so it's not practical from that point of view. But for now, we are not looking for a practical scheme. What we are looking for is a measure of uncertainty. And this scheme, as we'll see soon, is actually an optimal scheme, and it can offer us a measure of uncertainty. Okay, the number of bits represented by used by the scheme can be thought of as a measure of uncertainty, and that's what we'll do in the next video. We'll build on this example to make somewhat more general theory.